Okay, so let us continue then now with Stefan. Please.
Okay, all right. Time for some more nice problems. So the first two I want to discuss is, the first one I just like it. I think both of them are representative of a larger phenomenon, but the first one also has a very clearly suboptimal inequality, and I'd like to have the sharp form. This, don't worry, this is just the last slide. This is unrelated. So before going to the next slide, let me discuss a very nice simple problem. We're given a function on the 2 torus. And assume anything that you want, C infinity. It's not about regularity, okay? It's a nice little problem. And now what we're going to do is we can think about closed geodesics on the 2 torus. These are not very, very complicated. And one example would be this one, right? And it's like the video game geometry, right? So this happens to be a closed geodesic, and of course you can always unfold the torus, and when you unfold the torus, you just make it periodic. You realize these closed geodesics are just starting sort of one lattice point and moving to another lattice point, and then translations thereof, right? So we know everything in the universe about closed geodesics on the 2 torus. They're completely explicit. And they're just, you can count them, you can enumerate them. So one question you could now ask yourself is, what if you try to maximize the average value of the function? Average means you have to divide by the length of the geodesic, and you take a supremum over all closed geodesics. It's an optimization problem you may want to consider. And in fact, I didn't just wake up one morning and wrote this down. So this came up in related problems. At some point, there was a problem of this nature that had to be solved. In fact, was this one. So we had, this is the paper with Diogo and Felipe from 10 years ago. Time flies. So the function we had is exactly this function, and the problem was exactly this problem, right? It's plus and minus 1 functions, and you have closed geodesics, and you try to maximize it, and we did it by brute force. Because Diogo had a formula that's very nice, and it worked for plus minus 1, and it solves the problem. So the question is now, what's the bigger picture here, right? What's the more general framework? Is there a more general framework? And the answer is yes. And I found surprising because there's infinitely many closed geodesics. Right? There's a countable number of lattice points, and then for each lattice point you get one of these sort of geodesics, and then you have an uncountable number of translations, right? You optimize over a pretty big set, right? This is a pretty big set. But there is one thing that helps you, and the thing that helps you is when the geodesics get very, very long, they fill up the space in a very regular fashion. Right? They become very well distributed, and you'd expect that if the geodesic is long, that integral is going to be pretty close to the mean. It's like almost like numerical integration, right? As you get then more and more uniformly distributed, you're going to get closer to the mean, and then when you get close to the mean, you're not going to maximize anything because you're going to get the mean. So what you want is sort of deviations from the mean, and those you can only get with short geodesics. That's the idea. And that's the idea. That's all. And the question is, can you turn this into a result? And the answer is yes, but it's not the result I want. So the result looks like this. It actually has a very simple proof. If I didn't want to tell you about all the problems, I would tell you about the proof, because it can be done in 5 minutes. It's L2, and then some Poincaré inequality, and that's it. It's not very complicated. But it turns out you can get a bound on the length. So this is the point I want to emphasize. This optimization problem, you have to have mean value 0 for sort of trivial reasons. Okay, let me tell you the trivial reasons. What's the enemy? The enemy would be something like you have a function that's 1 plus a very high frequency sine, right? So you take something like 1 plus sine 10 to the 100x plus y. How about that? And then you multiply this by 10 to the minus a trillion, right? So that's an extremely smooth function from sort of a Sobolev notion until you go to high derivatives. At high derivatives, it's a rough function, but at the first or second derivative level, this is extremely smooth. But the maximum you actually attain by following, you set this equal to 0, and you get an extremely long geodesic. So it turns out this is maximized when the sign is 1. So you can create arbitrary, the optimization problem has arbitrarily long solutions if you violate the mean value 0 condition. Then the argument doesn't hold. But the moment this is not true, the moment your function is this, you can bound the length of the geodesic that you get, even for some arbitrary power, you can bound it by essentially the growth of the derivatives of the function. So it's a very clean Poincaré type inequality. It says if the function doesn't oscillate too much, the heuristic I gave you forces the solution of this problem to have a short compact solution. It's a sort of a very subtle way of inducing quantitative compactness, which I found was surprising. So why am I telling you about this? Well, it's kind of funny. That's one. But the other reason is I think it's the wrong result. So I think this proof is it's losing a derivative that it shouldn't. I think this term should not be here. And for scaling reasons, one of the L2 powers should not be here. I think this is the correct result. I don't know how to prove it. That's what I'm telling you. But I can also tell you that my proof is not very complicated. I mean, I tried to, of course, find the gaps, with the slackness, what am I missing? I didn't find it, but I do think that this is true. I do also want to advertise the underlying phenomena, which I think is really interesting, right? It's a form of geometrically induced compactness for a really hard optimization problem. That's the question of how to do higher dimensions, and if you go through my proof, you get some result, but my result is not sharp in 2 dimensions, so there's no reason to do it in 3. You can if you want to, but ideally it would be nice to have sharper results in higher dimensions, and I do think there is a version of this in sort of more abstract groups. I think there's more geometry that could come into play. Maybe not Rn, because the geodesics on Rn are just, it doesn't make sense, but if so there might be compact manifolds that are nice enough, that have sort of nice geodesics, or there might just be groups and you have subgroups or cosets of subgroups. And I think this is a phenomenon that may just translate to this more general setting. Okay, cool. All right, so next one, yes. Okay, so the next one is of a similar flavor, but there's 2 different motivations. And one motivation is going to be on the next slide. The other motivation is actually okay, you're going to think it's stupid, but I like astronomy, so sue me. So the problem is the following. You got the planet Venus, okay? And Venus is very, very hot, right? Surface temperature is like 500 degrees, but people didn't notice, so they sent probes up, and the probes would land, and they would immediately melt in like liquid methane that's 500 degrees. But people actually thought for a while it's the aliens turning them off. Right, because it's reliably like they land, and then 20 seconds later they stop sending, and people are like, these aliens don't want us to see what's going on. But okay, I can tell you think it's stupid, but okay. So here's sort of a fun question, right? So suppose for Fourier analytic reasons that Venus, the surface is a 2 torus, okay, but suppose there's no methane and it can actually land, so you land the rover, so the rover's here. And now you try to understand what the terrain looks like, right? Is Venus very, very flat? Or are there a lot of mountain ranges? Well, it's a question you could ask, right? But we already know from even just from telescopes that there's a big cloud on Venus you don't see very far, right? So this rover really doesn't see anything. Maybe it sees 10 meters, right? So you can't really tell whether there's mountains in the distance. You can only see what's in front of you. So what you could do is you could start driving around and measuring whether you go up or down. Okay, if you go up and down a lot, there's some mountains. Very good. But suppose you don't go up or down, you stay pretty flat. Does this mean that there are no mountains? No, it doesn't. Because maybe you're trapped between a valley, right? I mean, maybe I'm driving my little rover right here on the toroidal planet Venus, but the mountains are right here. and maybe there's a big valley here and a cliff, and I just happen to avoid all the cliffs, and I'm unlucky. This could happen, right? But the idea is if I keep driving my rover, ultimately I should find the mountains and the valleys. Is there a quantitative version of this? So that's the question. That's one motivation. Now let me give you the other motivation. If you have questions on this, I will not take them, okay? I'm not going to answer any questions about this. I think you see why. Okay, here's the other motivation. There's a very fundamental inequality, and it's true almost everywhere, and it's very easy, and it says if you have a function on the 2 torus, I'll stick with the 2 torus, with mean value 0, then the altunum of the gradient is at least the altunum of the function. Poincaré's inequality. And on the 2 torus, the constant happens to be 1. The proof is 2 lines. The proof is this, right? You expand it in Fourier series, you do Plancherel, you get the altunum is this, and then the altunum of that is the same thing with weights, and the weights are at least 1. And not a very sophisticated argument, right? And it's not meant to be, right? It's a useful tool, and you use it sometimes, and it's very powerful. If you have some bootstrapping argument, it can be very nice. But the question is when your extremizers are trivial, you see from the proof, extremizers require you to have frequency 1. Everything's obvious. Near extremizers have to be mostly frequency 1. Everything's open, right? This is clear. So the question is there a version of this inequality that's kind of scale invariant in frequency? Is there one that's not entirely trivial, but still captures some of the geometry? And it turns out the answer is yes. And it looks very, very funny. I'll tell you more about the numbers, but it turns out what you can do, and this is back to the rover. So Poincaré, the way we usually think about it, do I use U or F? F. The way we think about it is this. But it turns out there is an inequality that goes as follows. Instead of writing the gradient twice, you write the gradient once. And then the second gradient that you need for scaling that Poincaré has, you replace by a directional derivative in a fixed direction. Okay, so the gradient gives you the direction of the change in the function along the steepest direction, right? The gradient is smart. The gradient looks in all directions. This is dumb. This only looks in a fixed direction. So this would be the direction the rover is driving in. Okay, so it turns out this is one of these examples here. So this would be the 2 torus. You have the direction would be 1 and the golden ratio. And it turns out this inequality is true. Now what's funny about this inequality is the minimizers, actually I don't know what the extremizers exactly are. One could probably figure it out. But there's an infinite family of extremizers or near extremizers at every frequency scale. So what you've broken the trivial minimizer of the parabola. And it becomes much more interesting. So if you take a function that's given by a sine of Fibonacci numbers, which come from the continued fraction expansion of the golden ratio, that's not very mysterious, and you compute what the left-hand side is, the left-hand side is the right-hand side, so this is the fn squared. The constant is this thing, and that actually converges to 1 over squared 5. So this tells you this constant up here has to be at least 1 over squared 5. Or at most 1 over squared 5, but it also tells you up to constants, these guys, the left and the right hand side, are comparable in every sort of Littlewood-Paley band. You can find such an example. So in some sense, it's breaking Poincaré to stop it from being trivial, and you start getting this infinite family. And there's a couple of other things that are fun about this. So you could say, why did I write the golden ratio? Surely it's just an irrational number, but it turns out this statement is false if you replace this number by E. Even though E is also irrational. And it's unknown whether it's true with pi, but it's probably not. Okay, for the experts in the audience, this is just the badly approximable numbers. It's not mysterious. I mean, whether pi has bounded continued fraction expansions is mysterious, but probably not. Not too mysterious. Everything generalizes to higher dimensions. You don't do anything. It's not work. The problem with the argument is the proof is too easy. The proof, you just do it, the trivial proof I gave you for Poincaré, you do it with this, and then you open a number theory textbook, and you realize, oh, it's all in there. I need this is all there. This is great. Everything works, right? So the proof is fantastically easy and simple, but it's so easy you don't get a good handle on the mechanism beneath. So the thing I'm trying to advertise is I think there's a general version of this on general manifolds. And probably a large number of different versions of this. I mean, I think there's a lot of work that could be done here. So let's make it precise. I mean, let's go back to Venus, right? Venus is roughly round. Maybe it's got a little bump. Right? And the question is, Poincaré is still Poincaré. The proof is the same. Poincaré on manifolds is not much more complicated. Getting the constant might be hard, but so what? The question is now, can you do exactly the thing we just did? Can you take a little bit of the Poincaré power, so instead of having a 1 here, you have a 1 minus delta, and instead of having a delta power on the gradient, you put the delta power on the directional derivative. And do you get something like this? At what level of generality? For what manifolds is there a vector field? Given a manifold, what's the best vector field, best as measured by delta? And the idea would be something like, well, how would an inequality like this fail? It would fail if we already know by Poincaré, this thing's going to be bigger than that thing, right? With a 1 minus delta. The only way this inequality can fail if this is unexpectedly tiny. Unexpectedly tiny would mean that along the vector field, the function is essentially constant. Well, yeah, I mean, this happens, right? I mean, this happens right here for the suitably chosen sign. You're constant along very long geodesics. But if the vector field is kind of a friendly vector field that does a good job when it comes to exploring the manifold, right? If it goes everywhere, like this geodesic flow does, right? I mean, this actually explores the torus extremely well. If you have that and you're constant along that thing, well, the function would be constant, but it's got mean value 0, then it would be kind of 0, but it's not 0. So that's the contradiction, right? If you're not 0, but your mean value is 0, you'll go up and down somewhere. And if the vector field explores everything well enough, you should be able to pick this up along the flow of the vector field, unless you have extreme spikes left and right, like very tiny mountain ranges that are millions of miles high. But in that case, the gradient helps you. There's still a gradient term. So I think this is a really, really cool question that I like a lot. There's a problem on S2, right? I mean, the sphere is the next natural example, but there's the hairy ball theorem telling us any vector field on S2 vanishes in a point. What happens if you vanish in a point? The exploration stops. Still, you do have the gradient term. You should be able to kind of do it. Okay, lots of problems here, right? Presumably, the power depends on the mixing rate of the flow. So it turns out the geodesic flow with badly approximable ratio on the torus is the best when it comes to exploring the torus quickly. But if you were to take, E or pi, the inequality I wrote down would not be true, but if you change the power just a little bit, it would be true. So I assume that the delta, the larger delta, the better the vector field is. And there's a bold conjecture one can make. And the conjecture is, I think that delta cannot be larger than 1 over the diameter of the manifold, dimension of the manifold. I think just from the torus, this is what you see in the torus. It kind of feels right. Well, it kind of feels right. Yeah, I mean, if I had a proof, I'd tell you the proof. I might also be wrong, but so I think this is a really, it's geometrically very interesting. There's a hint of dynamical systems. The torus case is number theory. It's a very nice, I think, and it would break Poincaré from being something that's just useful at low frequencies and would give you sort of a nice general Poincaré that says, hey, there's actually a lot of fluctuation along these flows. Okay, questions? Excellent. Okay, let me tell you about another problem that's super fun that I don't recommend anyone works on, but then the second part, yes, you should work on the second part. So Hadamard has this very, very nice paper, and he says, hey, if I have a matrix, and I know that each entry of the matrix is at most big delta, I mean, that's what he chooses. How big can the determinant be? And there is a very famous inequality, and the inequality is Hadamard's determinant inequality. And the proof is kind of easy, because you do Gram-Schmidt. Okay, so it turns out the worst case, you go through a proof, and it's fairly elementary. And the thing that's interesting about the inequality is the case of equality. So the case of equality requires that each entry is plus or minus 1, and that all the columns are orthogonal, so when you do Gram-Schmidt, you don't lose anything. So the question is now, when do you get matrices that have plus minus 1 entries and have mutually orthogonal rows and columns? And this is, of course, the famous Hadamard matrix problem, and it's the most natural form of an orthonormal basis in a sense, because 0 and 1 is kind of breaking the symmetry, but plus minus 1 is in fact doing the symmetry. And of course, it has millions of applications in coding theory and packing, and it's a very nice object. And here's some examples. The question is now, here's a bigger one. So fun fact, I found out while researching the history, in fact, Hadamard actually immediately refers to Sylvester, and Sylvester actually introduced Hadamard matrices before Hadamard. And Sylvester also had, he wrote a paper about it that probably has the best title. I mean, today you couldn't get away with a title like this. The referee would just, they're merciless, these referees. So that's the title. I mean, it's like, thoughts about good and evil and everything reasonable under the sun. We kind of lost a little bit of that style. So he's introducing it. And it's published in the Philosophical Magazine, right? So, yes. 3 cheers for Sylvester. So anyway, he sort of introduces this. He points out there's a tensor construction. So if you have one Hadamard matrix and you tensor it, an n by n Hadamard matrix gives rise to a 2n by 2n Hadamard matrix, and this is not too hard to see. So we know there's infinitely many Hadamard matrices. And the question is, what about other values? And there's also a theorem that probably goes back to Hadamard. Maybe Sylvester knew it too. Maybe I shouldn't have written Hadamard, but there's a very nice proof, which I'm not going through, but it's elementary undergrad reasoning. You look at the first 3 rows and you use the symmetries and you're done. So you realize a Hadamard matrix can only exist if 4 divides n, except for this example with 2. 2 is sporadic, right? But okay, so far so good. So this is a very famous problem in combinatorics. Unless you have a really good idea, I don't think you should work on this. I was never even tempted to work on it because no ideas. But there's a reformulation, and that came out 2 years ago, and the reformulation goes as follows. It says, hey, a Hadamard matrix is really a matrix that's just plus minus 1 entries, and it's rescaled orthogonal matrix, right? It preserves, the fact that all the rows are orthogonal means it's an orthogonal matrix. You preserve the norm. So one way to think about a Hadamard matrix is really this. Plus minus 1 entries and not changing the norm of the vector. It's just a rotation of space. And when you think about it like this, you could ask, well, can I get things that almost do this? So we know already Hadamard matrices only exist when n is a multiple of 4. 11 is not a multiple of 4. I'm not going to find an 11 by 11 matrix that does this. But the question is, could I find an 11 by 11 matrix that almost does this? And the answer is yes, up to a constant. And the constant does not depend on n. So I think this is a really cool, I think it's a really cool way to take this combinatorial problem that we know is very, very hard and rephrase it and break it up in a way that makes it accessible to more quantitative tools. You can now measure progress by the size of the constant, for example. And I played with this, and I found out there's a simple trick how you can actually show that not only can you do this, but you can find this matrix even presupposing a circulant structure. So what are circulants? Circulants mean you fix the first row and all the other rows are just shifts. So this is, of course, a much smaller space of matrices, and the way I like to think about this result, and I'll show you the proof, which is trivial, and I owe it partially due to IMPA in a way that I'll explain in 3 minutes. What this means is there's many matrices like this, right? Because if you have n by n matrix and you have plus minus 1 choice, you have 2 to the n squared options. And what I'm telling you is there are good options using only 2 to the n. It's a much smaller search space. So if you drop the circulant condition and you just look at general matrices, there should be many like this. Let me give you the proof. Proof's very simple. Circulant matrices are diagonalized by Fourier. Right? Standard Fourier system is eigenvectors of all circulant matrices. That's pretty nice. There's a completely nice formula of the eigenvalues. So what you really have to do is you're given a polynomial induced by the entries of the first row, and you evaluate this polynomial at the roots of unity, and that gives you the n eigenvalues. Okay, now what we're going to do is we're going to try to understand, how much distortion can happen, right? What's the, among all vectors of size 1, how much can the matrix blow up or shrink it, right? We want that ratio to be as close as possible to 1. And we know it can't be 1 if n is not a multiple of 4, right? It's not possible. Well, you just go to the eigenvalues instead. Eigenvalues are just, the maximum value to root of unity and the minimum value to root of unity, and then you do the big jump and you say, you know what, I'll just look at the entire unit circle. Big jump, right? I'm losing a lot here. The question is now, is there a polynomial with plus minus 1 coefficients that is nearly constant on the unit circle? That's the question. And it turns out I'm not the first person to ask this question. So Littlewood asked exactly this question, and I also don't need to answer this question because it was answered. And I think Rob Morris is at IMPA. So thanks to IMPA for providing that crucial ingredient. So it's really, you can think of this as a corollary of that result. Right? That result really implies the existence of circulant approximate Hadamard matrices, which is fun. But the thing that I want to ask is, are there any nice, simple examples of approximate Hadamard matrices? And drop circulant. I mean, I think the circulant problem, I think, is still interesting because it should be easier than the Littlewood problem, because for the Littlewood problem, I dropped the roots of unity constraint and I went to the entire circle. So the circulant approximate Hadamard problem should be strictly easier than Littlewood, but Littlewood's pretty hard. So maybe not, but drop circulant, make it not circulant. So the non-circulant problem should be much easier because the circulant problem has a solution. You go from n variables to n squared variables. Life should become a lot easier. Now, so the Dong-Rudolph paper, they don't track the constant, but the construction actually uses ideas of Paley. So we're back to classic Fourier analysis. Paley built Hadamard matrices for certain prime indices. And Dong and Rudolph showed that you can glue them together in a sort of a sophisticated way. They didn't track the constant. Maybe one can track the constant. Question is there a nice construction? A simple one that uses only very basic ingredients. I mean, the other question that I think is really kind of relevant is we know now that I can find matrices with plus minus 1 entries that don't distort too much. So here's a constant, and it's the same constant here, and the constant is independent of n. But the question is really, I mean, can you write something like 1 plus 1 over log n? Like, it's not going to be 1. Hadamard tells us it's not going to be 1 for generic n, unless it's a multiple of 4, then probably yes, it is 1. But this is a very, very, I mean, I love the Dong-Rudolph paper because it's such a creative reformulation of a hard combinatorial problem. If I can solve it if n is a multiple of 4, and I'm in really high dimensions, surely I should be able to almost solve it if I'm not a multiple of 4. Right? Just go to the next multiple of 4, take that Hadamard matrix if it exists, which is a famous open problem, but modify it a little and you're good, right? You should be able to get almost isometries in all dimensions. You break the algebraic condition, right? I mean, the fact that it's an isometry is a strong algebraic condition. This is a relaxed analytic condition. The world should open up. That's the hope. How long do I have?
20 minutes.
20 minutes, perfect. Okay, questions on this? Okay, so our next problem came out of trying to solve this problem. And it failed in a really interesting way. Let me show you how it failed. So one very nice orthogonal matrix is, of course, the Fourier matrix, right? Super nice. Orthogonal, cosines. There's a whole bunch of these discrete cosine Fourier transform matrices. They're all discrete Fourier transforms, JPEG, wavelets. We know everything. The problem is they're not plus minus 1, right? I mean, the cosine is sometimes plus minus 1, but not always. So what's the trivial way to proceed? Well, you just take the sign, right? Okay, you're laughing. Maybe it's a dumb idea, but okay, I tried it. It doesn't work. In a weird way, if you play with it a little, it seems to almost work. Like the constant that you get is not a constant, but it's like square root log n, I think, or log n. I couldn't prove that. That's a cool problem. But yeah, I tried that, right? And then if you have an almost isometry, what happens is you can rewrite the matrix and you realize, okay, almost isometry just means that A transpose A has to be very close to the identity matrix. So what I did is I wrote this matrix down and I computed A transpose A and I thought maybe it's close to the identity matrix. Turns out it's not. But I plotted its large entries. So ready for the picture of large entries of A transpose A for this matrix? Here's the picture. So this is for n equals 100, and you see some stuff's happening, right? There's some lines, and there's actually some bouncy ball trajectories. You see the bouncy ball trajectories, right? So, or maybe I'm imagining this, right? You stare at pictures for too long, you see all sorts of things. Well, this is 200. This is 300. This is like so this is joint work with François Clément, who pointed out that this is like the DVD logo. Remember? Back when we had DVDs, it would bounce like this, right? So you start seeing these funny pictures, and the question is what's going on? And it's not going away. It's actually there.
What do you mean by large in this case? Really so
well, 500 is pretty large, no? If you think 500 is small, yeah, I'm going to ask you for 500 reais right now.
Well, I mean, your cutoff.
Oh, yeah. The cutoff, right. Good question. That's good. Yeah. So what's the cutoff? It turns out you get very interesting structures at sort of all scales that you cut off. But if I put the cutoff higher, you see the bigger lines more. And then as you drop the cutoff, you start seeing smaller lines pop out. And
so it's kind of that structure anyway.
Yeah, I'm not cherry picking a cutoff. In fact, there's a lot of microstructures we don't understand. Like, for example, you get like, you see like this weird semi-parabola thing here. You see the cross here, not entirely clear. So we played with this a little bit. I can tell you one result, and that result is short and simple and fun, and it requires n to be prime. And then, these are the entries of the matrix. If you write them out, it is the inner product of two orthogonal vectors after they've been signed, right? Without the sign here, this would just be cosine matrix entries, and inner product is 0, and now I'm forcing each entry to be plus 1 or minus 1. I'm taking inner product. This is the object you have to control, and this turns out satisfies a whole bunch of funny things, but one of them is if you introduce a sort of a norm in the finite field as the distance to 1, then you get some sort of funny identity, which is only useful when this object is small, but when A inverse B is almost, is a small number, this is a large number. This is a large, the entry is large, and this explains, what this explains is it explains these guys. It explains these trajectories, of which there are many, right? There's a second one here. See, this one is here. And more will pop out as you increase n. So these bouncy ball trajectories are explained. The round one here, I think we could explain by brute force. So we have an argument for the DVD box logo. But because n is not a prime number here, you start getting more stuff. But there are many more microstructures that we found ourselves unable to explain. Like it just gets very complicated somehow. But it's a lot of fun. Okay. Questions on this?
These are 500 guys.
500 guys. Okay, excellent. If you solve one of these, I'll we have several more technical results that are not so fun to explain. But it is clear that classic Fourier analysis works here. Like you can use it as a tool with one big formula, which probably, exponential sums start showing up. You control exponential sums, and it's fun. Okay. Yes. Well, I mean, we have really this result, right? I mean, this tells you if you want to be larger than epsilon n, this number has to be smaller than 1 over epsilon, which means you get, in the finite field, 1 over epsilon squared, many entries, right? So, you can get, this gives you a rough density result, but this error term is a bit too large to give you a classification or characterization. So if you say, what's the LP norm of the entries of the matrix, right, I cannot tell you. This gives you a lower bound, but the lower bound is presumably far from the truth. In fact, one of the more technical results is the only way for this number to be very small is if this thing here is large, if A inverse B is far away from 0, but if small multiples of A inverse B are also far away from 0. It's a bit mysterious, but it's fun. And this actually kind of generalizes in a way that we didn't expect. So at some point I said, let's do some examples. So take the Legendre polynomials. Okay, Legendre polynomials are orthogonal polynomials on -1, 1. They satisfy nice identities, everything's great. One natural object you may want to consider is exactly the same thing, right? What I told you is the Fourier matrix, or the Fourier basis on the interval, gives us a nice orthogonal basis. Now what I could do is I could sign that basis, right? You could sell this as machine learning, right? It's like sign, it's like ReLU, right? Sharp cutoff. You sign the basis and you see what happens to the orthogonality relation. Now I can show you this is what happens. So what I'm plotting here is I'm plotting in M and N the value of that integral. And you see on the diagonal it's 1, of course, because it's the same sign. You have this funky off diagonal. This is like slope a third, this is slope a fifth, this is slope a seventh. We didn't try to prove this. It also seemed to be true for all other orthogonal polynomials we tried. Fun. Slightly weird, but okay. And I have 13 minutes, so let's, unless there are questions. Maybe is that a questions? We're good? Okay, if you find all of this weird, let's become more canonical. So there's a very fun thing happening here. I'm not an expert on Kakeya, especially in this room. I'm even less an expert on Kakeya. But here's a very cheap Kakeya statement. It's not exactly the thing you think about when you think Kakeya, but it's the reformulation I want. One way to think about it is you have infinite lines, and they all point in different directions, right? They're not too aligned. And then what happens is if you thicken them a little bit, and I'm thickening it with chalk, right? The area of where two of them overlap is not too small. It's not exactly what you think about Kakeya, but sort of the 2D proof gives you a little bit this. So what happens here is I have 1 over n neighborhoods of n lines, and the lines are, no two of them are parallel, right? If I'm allowing them to be parallel, I'll just line them up parallel and they don't touch. There's no overlap. But if no two of them are parallel, any two of them will meet. And then what happens is you get this overlap condition here, and this thing is not too small. The trivial bound is the following, right? If two of them meet orthogonally, because then I have a 1 over n by 1 over n box. This object here is order, the area of intersection is 1 over n squared, and I have n squared intersections. The trivial lower bound is 1. And it turns out it can't be 1, it's log n. And that's one way of, it's very easy to prove this one. It's a cheap way of making it quantitative that there's not enough directions. You can't avoid too much, okay? What I like about this question is you can put it on the sphere. Notice I said. You can put this on, the formulation I just gave you doesn't require any geometry except lines and neighborhoods, right? Lines are geodesics. Lines on the sphere are great circles, right? S1s of maximum diameter. You take their 1 over n neighborhood and you ask how much does this neighborhood have to overlap? It's a question you can ask. So the trivial lower bound is, again, it's a 1 over n. The trivial lower bound doesn't change, right? A 1 over n neighborhood and a 1 over n neighborhood, if they meet transversally, gives you a 1 over n squared, and you have n squared interactions because any two great circles meet, because they can't be parallel because they're great circles. So this is the trivial lower bound. The trivial lower bound here is sharp. But there is a non-trivial sharp lower bound that starts happening when you go from L1 to L2. So when I'm squaring it, if I square this object, the trivial lower bound is 1 over n squared, because it's 1 over n squared. I'm squaring it. It becomes 1 over n to the 4. I have n squared terms. It gives me 1 over n squared. So the trivial lower bound is 1 over n squared. And what's happening here is that's not true. There is a log. And I claim it's philosophically exactly the same log. But the threshold, the transition happens at 2, not at 1. And what this means is even though the trivial lower bound is sharp, it is not true that all the overlaps are small. Some of them are quite large. Some of them are much larger than 1 over n squared. And you start picking it up when you go from L1 to L2. So there is a type of a Kakeya phenomenon on the sphere. And the reason, I'll give you the proof, because the proof's actually easy. Great circles are like equators. Equators have a north and a south pole. Okay? So you identify the north or south pole. There is a computation that's kind of painful. That's this. It turns out the area of overlap is proportional to essentially the distance between the corresponding north and south poles. Then we're back to Dima. We end up with a Riesz energy. It's not exactly the classic Riesz energy because the north and the south pole are the same point. So it's really Riesz energy in a Grassmannian. Fun fact, this was actually considered independently by Chen, Harden, and Saf. They looked at exactly the same object because it makes sense on the Grassmannian. They were not motivated by any Kakeya consideration, so I think it's a kind of a cool object because it shows up 2 different ways. And then you do fairly basic estimates. It's not very hard to prove that. So the question is now the following, right? What's the problem? The problem is we know L1 is trivial, and we know that if you increase p, you go up. And this is sharp for p between 1 and 2. And I'm willing to bet 500 AIs. Okay, you hear it's on record. Okay, you solve this, I give you 500 AIs. It's probably not sharp when p is bigger than 2. I'm sure. I'm willing to bet 500 AIs. I'm actually quite desperate about this, so maybe more. Feel free to haggle. I'd pay for this. I think if p is above 2, there's the phase transition, and what happens is you start caching in logs. Maybe logs, but it's not going to be 1 anymore. And this is a problem I like a lot. Questions about the problem? Okay. So the story that's happening here is really you go from R2 to S2, and when you sort of visualize this, what happens is the curvature, right? The curvature increases the transversality that's possible, and that's why you have a shift in sort of the critical LP index where you start picking up a Kakeya type phenomenon. But when you start wondering about this, I go from 0 to positive curvature and stuff happens. One funny question is, what if I go to negative curvature? Right, so you could have lines in the Poincaré disk, no 2 of them parallel, which means any 2 of them meet. You have an intersection. The thing is, I'm a bit scared of the Poincaré disk because it's like infinite volume, right? It's kind of like stuff's happening here that's kind of funky, right? The boundary. So but I think it's actually probably there is an analogous phenomenon in the Poincaré disk. And if everything goes according to plan, right, then the critical p index would go from 1 to like 0 or minus 1. I mean, there's probably some similar sort of inverse thing happening, which would give you like a sort of a multi-curvature Kakeya phenomena, which would be really fun. So this is an open. I haven't even tried this one because you got to know your limitations. So people who are very fluent in complex analysis or sort of conformal geometry, that's a good one. And I want to indicate that maybe this is a good way to finish in the last 5 minutes. I want to indicate that this might be hard for the following reason. When you go from, if you go on the sphere, right? If you go on the sphere and you have these sort of great circles, the way to get an improvement for p larger than 2 would require you probably, I hope I'm wrong on this, but there's a chance it might require you to control interactions between 3 or more great circles, right? If you just look at squares, you have to control all pairwise interactions. If you go p equals 3, you have to control all triples, and you have to show that at least some triples have some non-negative sort of overlap that generates more than the pairwise interaction does. So there's a good chance that this is what's happening. If that's what's happening, then the corresponding north poles on the sphere would be almost on a great circle. That's the geometry. Now if you go back to the plane, this is the question you run into. This question is, afterwards, after this talk, at the coffee break, come up to me and tell me if you've known this problem before, tell me. Because I think it's not very well known. This is the only description I found in the literature. It's the obituary of Jean Bourgain. And the problem is right here. So it says, he says the last problem he asked me is if you have n points in a unit square, such that, is it possible that you have n points such that no slightly thickened line contains more than a number? So I'm going to rephrase this. This is a little bit more, I find it a friendlier formulation. If you're given n points in the unit square, think of n as large. Is it always true that you can find 3 that almost lie on a line? Of course, for algebraic reasons, yeah, if you put n points randomly, no 3 of them are on a line. Of course not. Why would they, right? But the question is, can I thicken it a little bit? Can I thicken a line a little bit such that I contain 3 points? And the answer is, how much do I have to thicken the line? And there's a trivial argument that says if you thicken it by 3 over n, you're good. And here's the proof, right? If I have 3 over n, I'm going to look at this line here, and then the next line, and you have all width 3 over n. By pigeonhole principle, one of these n over 3 regions contains at least 3 points. I'm done. So it's a trivial pigeonhole direction. I'm not even using the fact that it's 2D. I'm using lines in one direction. This is currently the best possible result. This is the state of the art. I don't even know a proof that says you can replace 3 by 1. I once gave it as homework, and they came back with 2.9. So 2.9 you can give undergrads as homework. 1 I don't even know how to do. There's a big problem in our understanding of the plane that's very well encapsulated by this very simple problem. I mean, surely if I use lines that look in different directions, I should start winning, right? I should start getting a little bit. This is a hard problem, but it's very easy to state. Okay, questions on this? If not, then now is a perfect time to stop. Thank you very much.